the sky over America is not just dark anymore. It's twisted. On the radar wall, the country is exploding in color. A hook-shaped supercell spins over the plains, its core glowing white where hail is shredding wheat fields. To the west, a blue-green smear of snow slams into the Rockies. Farther south, a ribbon of neon red rain coils over California like someone dragged a paintbrush across the map and didn't stop. Above it all, one satellite frame freezes the real problem. A silver-white band of clouds tracing a jet of wind that no longer flows straight east, but dives, kinks, and whips across North America like a cracked whip. Now drop into one night of chaos. In Oklahoma, sirens wail under a green-black sky as a rotating wall cloud lowers over a town that has already rebuilt twice. In the Rockies, truckers crawl through blizzard conditions, their headlights swallowed by horizontal snow that was rain just 3 hours earlier. On a California freeway, orange streetlights reflect off moving water, not asphalt, as cars push wakes through what used to be a minor storm. None of these scenes are supposed to be connected. They are. They sit under the same warped ribbon of high-altitude wind. That ribbon has a name, the jet stream, a river of air 5 to 9 miles above the surface, often faster than 150 miles per hour, steering almost every major storm that hits the U.S. in a normal year. It's America's storm highway, a relatively smooth west-to-east flow that guides winter cyclones, spring thunderstorms, and summer fronts in an orderly train. That balance is the system working as designed. This year, the highway has moved. The jet is displaced south in one region, yanked north in another, and bent into deep waves that stall over the same states for days. Routine low-pressure centers that used to pass through in 12 hours now tap into warmer oceans, thicker water vapor, and extra atmospheric energy. That energy has to go somewhere. It goes into supercells that last all night, atmospheric rivers that sit over one watershed, and bomb cyclones that swallow half a continent. Forecasters saw the outline of this weeks in advance, watching Pacific charts light up with strange patterns. The upper-level winds over the ocean shifted. Temperature contrasts twisted. Model runs started drawing the same contorted jet stream again and again. That is a fact most people hear and immediately forget. Even the forecasters did not forget this one. They expected active weather. They did not expect $3 billion disasters in a single 48-hour window. The science is clear on this. When the jet stream bends and stalls, weather stops behaving like weather and starts behaving like infrastructure failure. Flood maps that assumed storms would move are suddenly wrong. Insurance models built on 20th century storm tracks quietly fall apart. What you call a normal season in your state begins to feel like ancient history. This isn't just a bad run of storms. It is the opening signature of a new era of American superstorms, written in the sky by an invisible river of air that has slipped its old banks and is still shifting. Pull back from the radar blobs and warning polygons on your local forecast. Zoom out until the borders disappear, until the whole continent shrinks to a single glowing shape under swirling cloud. Then keep going. Now the frame is the full Earth black space around a spinning blue sphere, and across the top of it a flickering white ribbon whips and coils like a live wire. That ribbon is the polar jet stream, a high-altitude river of air, 5 to 9 miles above the surface, racing at more than 150 miles per hour. It is the storm highway of North America. It quietly decides where the parade of low-pressure systems will go, which coasts get hammered, which plains stay quiet. That is a fact most people hear and immediately forget. In a stable climate, that ribbon runs in a relatively tight band from west to east. It wiggles, but it does not lose the plot. Cold, dense Arctic air stays mostly locked to the north. Warmer, wetter Pacific and Gulf air stays mostly to the south. That balance is the system working as designed. Now watch the satellite view again. The ribbon is different. It loops, stalls, and dives far south over America, then snaps back north in violent bends. Forecasters call this a more meridional or wavy jet stream. The simple translation: the atmosphere's steering wheel is shaking in your hands. This is not happening in a vacuum. The Arctic is warming 3 to 4 times faster than the global average, erasing the sharp temperature contrast that used to keep the jet tight and fast. At the same time, an overheated Pacific keeps pumping warm water vapor and extra energy into the lower atmosphere. A destabilized, increasingly wavy jet stream is now interacting with a supercharged Pacific and a rapidly changing Arctic. That is the central driver of a new class of American storms. When that high-altitude river kinks and stalls over one region, it locks in extremes. One town sits under a training line of thunderstorms for days and ends up in a billion-dollar flood event. Another lies just under the clash zone of air masses and sees record-shattering tornado outbreaks, the kind that redraw damage maps in a single afternoon. Farther west, the jet funnels back-to-back atmospheric rivers into California, turning mountain ranges into temporary reservoirs of unstable snow. In winter, those same jet stream contortions can spin up bomb cyclones that behave like hurricanes, 80-mile-per-hour gusts, coastal storm surge, whiteout blizzards wrapped around a warm, slushy core. Warmer oceans and air mean more water available for every storm, about 7% more water vapor for each degree Celsius of warming. That energy has to go somewhere. Lately, it is going into the sky above your head. The science is clear on this. These are not 2100 scenarios. This shift is unfolding right now, inside a single human generation, faster than infrastructure, insurance, and emergency planning can adjust their spreadsheets. Bridges built for 20th century floods are facing 21st century rivers. Power grids designed for yesterday's wind loads are starving down tomorrow's derechos. So the question is no longer whether the jet stream has changed. The question is what happens when the next round of Pacific warming pushes it even further out of its old lane, and which part of the map ends up directly under the new storm highway. That storm highway now runs straight over your life. Picture a mental map of America, not as flat colors on a screen, but as layers under a moving river of air. 5 to 9 miles up, the polar jet stream roars along at more than 150 miles per hour, steering almost every major U.S. storm. That balance is the system working as designed, until the river bends. Start on the West Coast. If you live in California or the Pacific Northwest, your front line is the atmospheric river. Warm Pacific water is loading the air with moisture. That energy has to go somewhere. When the jet dips south and locks in, it turns straight over your city, and those once-in-a-century flood maps start looking wildly optimistic. The same highway that used to deliver gentle winter rain is now dropping torrents that rearrange highways. Slide inland. Over the Rockies and into the high plains, mountain towns and ranchlands sit right under the clash zone. On one side, Arctic air still spills south. On the other, air warmed over the Pacific and the Gulf races north. Where the jet stream lines those up just right, supercells ignite. The difference between a breezy spring thunderstorm and a tornado swarm tearing across 3 states can be a subtle kink in the jet, hundreds of miles away. That is a fact most people hear and immediately forget. Keep going to the Midwest. Maybe you live in a suburb outside Omaha, Chicago, or Des Moines. Your backyard is where derechos ride the jet like a rail. A slightly shifted track can aim a 500-mile wall of wind directly at your neighborhood instead of 200 miles to the north. The same goes for winter. A wavy, stalled jet can park a bomb cyclone over the Great Lakes, turning a routine snow day into a blizzard that shuts down interstates and power for days. Now swing east. From Texas across the southeast and up through New England, the negotiation is about heat, humidity, and speed. A jet stream pulled farther north can leave the south in stagnant, brutal heat while funneling storm after storm into the Ohio Valley and the Northeast. Or it can dive south, dragging polar air into Atlanta while coastal New England drowns under back-to-back nor'easters. Your local risk of floods, blizzards, derechos, or tornado swarms is being quietly rewritten in the upper atmosphere. So the journey now follows that invisible river, from its birth over the Pacific, across warm ocean surface waters, into its collisions with Arctic air, and down into the storms that rip shingles off roofs and snap transmission lines. Then up again, into the climate models forecasters use to guess where the next bend will form. This is not a montage of random scary weather. The science is clear on this. A few degrees of warming and a warped jet stream can flip entire seasons upside down. The goal here is simple, a step-by-step breakdown of how the system is supposed to work, how it is breaking, and what that means for your specific corner of the map. By the end, you will know more than headlines. You will know what to look for on the weather map, the telltale dip, the stalled loop, the sudden northward jump that means your area might be next in the crosshairs. So if the goal is to read the map before the storm hits, this is where the map gets complicated. The jet stream is not an easy headline. It lives 5 to 9 miles above your head, it moves at highway to jetliner speeds, and it speaks in pressure gradients and temperature contrasts. That is exactly why it matters. Out of all the pieces of climate literacy you could pick up right now, understanding how the jet stream is shifting over North America is one of the most practical. It is the invisible storm highway for the United States. It decides whether that warm, moist Gulf air curves toward Dallas, Chicago, or New York. It decides whether an atmospheric river aims at Seattle or slides down toward Los Angeles. That is a fact most people hear and immediately forget. Down on the ground, it just looks like chaos. A line of supercells over Oklahoma, a derecho tearing across Iowa cornfields, a winter bomb cyclone wrapping New England in whiteout. Headlines about once in a century, weather that apparently arrives every other year. But high above those scenes, the same narrow river of air is bending, stalling, and looping in new ways. This channel exists to make that hidden machinery visible, to take the warm water in the Pacific, the rapid heating of the Arctic, the strange kinks in the jet stream, and frame them cinematically so you can see patterns instead of noise. Storms, blackouts, crop failures, insurance collapses, grid failures, they are not separate stories. They are different chapters of the same system. If that feels worth your time, this is the moment to support it. Tap like so the algorithm knows people care about more than dramatic radar colors. Subscribe so the next time forecasters say the jet stream is acting drunk, you know exactly what that means for your county line. Share this with the friend or relative who always talks about the weather, but has never really seen what is steering it. That support is not abstract. It funds deeper dives into the data, into the models that forecasters use to see a stalled jet pattern 10 days out. It pays for interviews with the people staring at those upper air charts at 3 a.m., and for visualizations that turn pressure fields and wind speeds into something you can feel in your gut. That energy has to go somewhere. The point here is to show where it is going before it arrives at your front door. The science is clear on this. The better the public understands the jet stream, the less surprise there is when the next superstorm carves a scar across the map. So now that the stakes are on the table, and you know why this river of air matters to your roof, your food, and your power, the story rewinds. The next step is simple. Strip it back to basics. How the jet stream is supposed to work, why that balance is the system working as designed, and how warming oceans and a changing Arctic are breaking it, piece by piece, from the ground up. Music swells. The low rumble of earlier storms fades out. The screen goes dark for a beat, then a clean title burns in. Why the jet stream shift is launching unprecedented superstorms across America. The sound design pulls you in. The noise of disaster steps back. The invisible architect of that disaster steps forward. Stay close. This is where the story really begins. High above your head, 5 to 9 miles up, there is a river of air moving faster than most cars on the interstate. A narrow band of screaming fast winds, steering almost every major storm that hits the U.S. That is a fact most people hear and immediately forget. This river has a name, the jet stream. There is more than one. In both hemispheres, several jets trace looping paths around the planet. But the one that matters most for your roof, your crops, and your insurance premiums is the polar jet over North America. That is the band currently behaving in ways that keep forecasters up at night. Picture a high-speed aerial highway wrapped around the northern hemisphere, running west to east. That highway is the jet. Low-pressure systems, winter cyclones, atmospheric rivers, even the seeds of supercell thunderstorms are the trucks and cars riding along it. Where the highway bends, they bend. Where it dives south, cold air follows. Where it arcs north, warm, humid air from the Pacific and the Gulf surges in. In a stable climate, the contrast between frozen Arctic air and warmer mid-latitude air locks that highway into a relatively tight, fast lane. That balance is the system working as designed. Storms race through, they hit, they move on. Misery, then recovery. Now interrupt that picture. The Arctic is warming 3 to 4 times faster than the global average. The temperature difference that powers a straight, strong jet is shrinking. At the same time, the Pacific and Atlantic are running record warm at the surface, pumping extra water vapor and energy into the lower atmosphere. That energy has to go somewhere. The result is a jet stream that meanders, stalls, and buckles into giant U-shapes and S-curves. The storm highway slows down. Lanes twist. Instead of a clean procession of weather systems, you get pileups. A winter bomb cyclone that would normally slam the Midwest and exit in a day can park for 3. An atmospheric river aimed at California can lock in place, turning one heavy rain event into week-long flooding. When that highway shifts just a few hundred miles, entire regions jump from drought to deluge, from quiet skis to tornado outbreaks. When it stalls, heat domes like the one that roasted the Pacific Northwest in 2021 can sit over the same counties for days. The science is clear on this. A slower, wavier jet raises the odds of extremes that feel less like weather and more like siege warfare. So the question is not only, what is the jet stream? You already know that now. The real question is, what happens to America when this highway in the sky keeps warping? To answer that, the story has to follow the bends, through the Pacific, into the Arctic, and down into the superstorms now riding this broken road. So before following those bends, there is one anchor point you need in your head. One fact that quietly controls almost every twist in that highway in the sky. The jet stream exists because the planet is unevenly heated. In plain language, it lives on the contrast between warm air closer to the equator and cold air stacked over the Arctic. That is a fact most people hear and immediately forget, but it is the closest thing this story has to a master switch. Here is the simple version. Warm air near the tropics swells and expands. Colder air near the poles is dense and heavy. That difference in temperature creates a difference in pressure. That pressure difference creates wind. High above the surface, about 5 to 9 miles up, those winds organize into a narrow river of air that can scream along at more than 150 miles per hour. That river is the polar jet stream. The bigger the temperature contrast, the sharper the pressure gradient. The sharper the gradient, the tighter and faster that jet. Picture a racetrack pulled taut between the equator and the pole. When the contrast is strong, the track is smooth and narrow, and storms race along it in a fairly clean line. That balance is the system working as designed. For most of the 20th century, that balance held reasonably steady. Yes, there were wild winters and quiet ones, blockbuster storms and boring seasons. But over decades, the jet stream's average position over North America barely budged. Storm tracks took familiar lanes, Pacific systems diving into the Pacific Northwest, clippers sliding out of Canada, nor'easters spinning up along the eastern seaboard. Farmers, forecasters, and entire cities built calendars around that rhythm. Now zoom in on the part that has suddenly become dangerous. The Arctic is heating up 3 to 4 times faster than the global average. Sea ice that used to reflect sunlight is vanishing, exposing dark ocean water that soaks up more solar energy and releases more warmth back into the atmosphere. The pole is catching up to the mid-latitudes. The contrast that powers the jet is eroding. When that temperature contrast weakens, the jet stream often slows and widens. Instead of a tight, fast racetrack, you start getting a looser, wandering river. The flow develops big north-south swings, like meanders in a lazy river cutting through a floodplain. Those are the ridges and troughs you see on weather maps, the exaggerated kinks that can drag warm Gulf air deep into Canada or plunge polar air into Texas. And here is the hidden twist. A slower, wavier jet is not just weaker, it can get stuck. The technical term is a blocked pattern, but the effect on the ground is brutally simple. Heat domes that park over the Pacific Northwest for a week and cook cities built for rain, not 115 degrees F. Atmospheric rivers that aim at California and do not move, turning hillsides into mud and valleys into inland seas. Winter storms that stall over the Midwest, dumping snow until roofs fail. That energy has to go somewhere. When the jet bends and locks, it stops spreading that energy out and starts concentrating it over the same regions day after day. More rain from a warmer atmosphere falls on the same watershed. More heat under a summer ridge bakes the same fields. More cold on the downstream side of a deep trough crashes into warm, moist air from the Gulf and spins up the kind of supercells and derechos that rewrite insurance tables. The science is clear on this. As long as the Arctic keeps warming faster than the rest of the planet, that master switch will keep nudging the jet into stranger shapes. The question for America is no longer whether the highway in the sky is changing. The question is what happens when those bends start to lock in over the same regions, again and again. Because that is where routine bad weather ends, and the era of entrenched superstorms begins. So to understand what it means for that highway to start locking in, you need to see how it works when it behaves, when it looks almost boring. Picture a factory floor suspended 5 to 9 miles above North America. Running across it is a fast-moving conveyor belt, roaring from west to east. That belt is the polar jet stream. Low-pressure systems and storm fronts are the packages, dropped onto the belt over the Pacific and carried across the continent on schedule. In a typical winter, that belt lines up in a relatively straight west to east lane. The jet dives in off the Pacific Ocean, taps into warm, moisture-loaded air, and guides a steady parade of storms into the Pacific Northwest. From there, it hops the Rockies, reforms on the plains, and sends one system after another marching through the Midwest and into the Northeast. To forecasters, that pattern is the background music of American weather. Not calm, but predictable. That is a fact most people hear and immediately forget. Slide that river of wind a few hundred miles north, and the story on the ground changes. Cities under the jets left flank feel milder Pacific air, more rain than snow, fewer Arctic blasts. The conveyor belt is delivering storms, but they are tempered by air that has crossed thousands of miles of relatively warm Pacific water before it reaches your backyard. Drop the jet south, and the conveyor belt now drags frigid Arctic air into the mix. The same low-pressure packages spin up into snowstorms, ice storms, or brutal cold fronts. A town on the warm side of the jet might be in a hoodie. 50 miles north on the cold side, it is -10 with blizzard conditions and power lines snapping. That balance is the system working as designed. A sharp temperature contrast between the frozen Arctic and the mid-latitudes powers a fast, fairly straight jet. That jet, in turn, decides who gets soaked, who gets buried, and who gets a deceptively quiet week. You feel that decision in everyday life, even if you never think about it. Farmers' time planting windows around dry breaks between jet-steered storm systems. Airlines plan routes and fuel loads around where that upper-level conveyor will speed them up or slam them with turbulence. City budget directors quietly hope the jet spreads snow events out over an entire season, instead of blowing the plowing budget in 3 back-to-back nor'easters. The science is clear on this. When the jet holds a stable lane, the chaos of individual storms adds up to a climate people can plan around. For decades, that storm highway over North America was variable but broadly reliable. It bent. It shifted. It misbehaved for a week, then snapped back. El Niño is what happens when that balance breaks over the Pacific. A warped jet is what happens when that break migrates into the heart of the continent. So what happens when that once reliable conveyor belt starts buckling like a warped train track, and the packages stop moving on? That energy has to go somewhere, and increasingly, it is going into supercharged, stuck superstorms parked over the same communities, again and again. So picture that conveyor belt from the last section, but zoom out. On the left side of your screen, the jet stream is a clean arc racing west to east across North America, a tight ribbon of 150-mile-per-hour winds 5 to 9 miles above the surface. Storms hop on, ride across the continent, and move on. That balance is the system working as designed. On the right side, the same ribbon looks broken. It plunges deep into the Gulf of Mexico, then lunges north into Canada, then dives again over the Atlantic. Huge southward dips, tall northward bulges. The once smooth highway now looks like a derailed train track drawn across the sky. That is a fact most people hear and immediately forget. Those bends have a name: large-scale atmospheric waves. Scientists call them Rossby waves. They are not new. They are how the planet naturally shuffles heat between the equator and the poles. But the background is changing. The Arctic is warming 3 to 4 times faster than the global average, shrinking the sharp temperature contrast that helps keep the jet stream tight and fast. Slow the river and the meanders grow. Here is the important shift. It is not just that the jet is wavier. Those kinks are becoming more amplified and more persistent. The waves dig deeper, then refuse to move. The science is clear on this. More blocked patterns are showing up in reanalysis data and in climate model projections. The highway does not just twist, it stalls. You have already seen what a stalled wave can do. In June 2021, an enormous northward bulge locked over the Pacific Northwest. Under it, sinking air compressed and heated day after day. Portland hit 116 degrees F. Lytton, British Columbia, reached 121 degrees F, then burned. Meteorologists called it a heat dome. In the upper air, it was a Rossby wave parked in place. 2 years earlier, in 2019, a different block parked the jet stream so that storm after storm rode the same track over the Midwest. Warm, moisture-loaded air from the Gulf kept slamming into that stalled boundary. Rivers in Nebraska, Iowa, and Missouri swelled beyond levees. Fields became inland lakes. The pattern did not have to be dramatic to be devastating. It just had to sit there. Flip the sign, and the opposite happens in the west. A stubborn northward bulge deflects Pacific storm systems away from California and the southwest. Atmospheric rivers that should deliver winter water to reservoirs instead arc into Canada. Year after year, drought deepens, forests dry, and any spark can turn into a megafire. El Niño is what happens when that balance breaks over the Pacific. A warp jet is what happens when that break migrates into the heart of the continent. Meteorologists sometimes call this the drunk jet stream. Not because it is random chaos, but because the system is losing some of its tightness. The jet wobbles more. It staggers. And when one of those exaggerated bends lines up over your region, the weather above you can lock in heat, floods, blizzards, far longer than you are used to. So here is the uncomfortable question. If the jet stream is wobbling more often, what happens when one of those deep dips lines up perfectly with all the ingredients for American superstorms, and then refuses to move? When that deep dip locks in, you do not just get a bad thunderstorm. You get a storm that behaves like a continent-scale machine. Call it a superstorm. Not a single Hollywood monster with one eye in the middle, but a sprawling, linked outbreak that rolls across time zones. Tornado swarms carving parallel scars through farm fields. Flash floods turning interstates into rivers. Blizzard conditions on the cold side, hurricane-force winds on the warm side. All from the same connected system, feeding on the same distorted jet. To understand how that happens, you have to look up, way up, about 5 to 9 miles above the surface. Up there, the jet stream becomes more than a steering current. It becomes life support. A powerful jet overhead acts like an industrial exhaust fan for storms. Rising warm, moist air from the Gulf surges upward in towering thunderstorms. The jet grabs that air at the top and yanks it away, clearing space so more air can rise. That is a fact most people hear and immediately forget. In meteorology, that exhaust fan is called upper-level divergence. Plain language, the top of the storm gets ventilated. The more efficiently the jet clears out that air, the taller and more intense the storm can grow. Supercells, the rotating thunderstorms that spin up the strongest tornadoes, absolutely thrive on that. So do derechos, those long, bow-shaped walls of wind that can race across multiple states overnight and leave a damage path longer than some countries. Now imagine the jet has dipped south, draping those strong upper-level winds directly over a corridor of warm, humid Gulf air at the surface and sharp temperature contrasts along a stalled front. That is the overlap that keeps forecasters awake at night. Warm water in the Gulf loads the lower atmosphere with moisture. A cold, dense air mass slides down on the north side of the jet. Between them, a razor-edge boundary. That balance is the system working as designed, until the jet intensifies overhead and pulls the whole setup into overdrive. The jet does more than just intensify storms. It organizes them. Picture a messy blob of scattered thunderstorms over the plains. On their own, they pulse up and die. Now place a screaming jet streak above them. The upper winds grab those bubbling towers of instability and stretch them, line them up, carve them into long, arcing squall lines. The jet stream becomes the sculptor's hand, shaping chaos into a single, coherent structure that can march from Oklahoma to Ohio before sunrise. That energy has to go somewhere. In a shifted jet regime, it goes into bigger gradients, faster spin-ups, and more violent transitions. Atmospheric rivers slamming the west coast, winter bomb cyclones exploding off New England, spring severe weather outbreaks that show up a month early or a month late. None of that is random noise. The science is clear on this. In the next sections, the camera will move from this bird's eye view down into specific cases. The atmospheric rivers that turned highways into canals, the bomb cyclones that deepened faster than some hurricanes, the spring outbreaks that hit regions that thought their season was over. The patterns do not match the old playbook anymore. The jet moved. The storms followed. The question now is who is standing underneath the new storm highway. That new storm highway is not steering itself. Something is feeding it, shaping it, and in some cases overclocking it. The jet stream does not exist in isolation, hanging in the sky like a loose cable. It is wired into a global engine where the oceans do most of the heavy lifting. Over 90% of the excess heat trapped by greenhouse gases has gone into the oceans, not the air. That is a fact most people hear and immediately forget. But that hidden heat is the fuel source for the atmosphere you live in. Think about how different water feels from air on a warm day. Air heats up and cools down quickly. Water does not. It stores energy. It moves that energy sideways and downward, then releases it back to the surface slowly, through evaporation and convection. That energy has to go somewhere. When it finally comes back out, it shows up as warmer nights, heavier downpours, and storms that seem to find an extra gear just when they should be winding down. Warmer oceans mean a warmer baseline atmosphere sitting on top of them. Warmer air can hold more water vapor, roughly 7% more per degree Celsius. More vapor means more fuel for storms embedded in the jet. The same system that once produced a cold rain now produces a tropical-style deluge. The same winter pattern that used to rebuild mountain snowpack now delivers wet, heavy snow followed by nights that never quite cool enough to lock it in. That balance is the system working as designed. The balance is shifting. Temperature gradients are what give the jet stream its shape and speed. Cold to the north, warm to the south, a sharp contrast in between. Rapid Arctic warming is weakening that contrast, but the oceans are not warming evenly. Patches of extra warm water in the Pacific and Atlantic are changing where the strongest gradients set up, and the jet follows those gradients like train tracks. Zoom in on the Pacific. The belt of sea surface temperatures along the equator can quietly tug the jet stream north or south, strengthening one branch over Alaska while starving another over the southern U.S., a slightly warmer patch near the date line, a slightly cooler tongue off South America, and suddenly, the storm highway into California lifts toward the Pacific Northwest, or drops toward Baja, leaving someone high and dry and someone else under a fire hose. Picture the Pacific as a giant bathtub. Shift the heat in one corner and the whole surface starts to slosh. The atmosphere feels that slosh. High-altitude winds realign. Storm tracks bend. El Niño is what happens when that balance breaks in a very specific, very powerful way. El Niño and its cold sibling La Niña are the big slosh events. They are the moments when the warm water piles up, tips, and sends a pulse of energy across the Pacific that can yank the jet into a new lane over North America. Forecasters are now watching those cycles unfold on top of the warmest background ocean ever recorded. The question is not whether the jet will respond. The question is how violent that response becomes in the years ahead. Those violent responses do not begin in the upper atmosphere. They start at the surface, under a blazing sun, in air so warm it can barely sit still. Picture the equator at noon. The sunlight is almost straight overhead, pouring energy into dark ocean water and land. The surface heats up. The air above it warms, expands, and rises in massive slow-motion towers. That rising air has to go somewhere. At high altitude it spreads out toward the poles, then cools and sinks again in the subtropics. That giant conveyor belt is the Hadley cell, one of several stacked circulation cells that quietly move heat away from the equator every hour of every day. That is a fact most people hear and immediately forget. But those cells are the scaffolding for the storm highway over North America. Now add rotation. Earth is spinning underneath this north-south flow. As air moves poleward or equatorward, the Coriolis effect bends it, turning those straight-line motions into east-west winds. Near the surface, that helps build the trade winds and mid-latitude westerlies. High above, where air from warm and cold regions rubs shoulders, the contrast sharpens. The sharpest contrast sits where frigid polar air meets milder mid-latitude air. That temperature clash focuses the wind into a narrow, fast corridor, a band of winds 5 to 9 miles up, often over 150 miles per hour. That band is the jet stream. Think of it as an invisible guardrail between air masses, a guardrail that also doubles as a highway for storms. Vertically, the jet is not a flat ribbon. It is thick, with the strongest winds near the tropopause, the boundary between the turbulent lower atmosphere and the more stable layer above. Below that, winds weaken, but the jet usually sits right above the frontal zones at the surface where storms are brewing. A low-pressure system deepening over the plains. It is often being ventilated by that high-altitude river of air, like a chimney drawing smoke. That energy has to go somewhere. You feel this even if you never look at a weather map. Airlines plan routes to ride the jet eastbound and dodge it westbound, shaving hours and fuel when they hit that fast tailwind, or bouncing through clear air turbulence when they misjudge its edge. Farmers in Iowa or Georgia stare at long-range forecasts, trying to guess where that storm corridor will park before they commit millions of dollars in seed. Utilities track typical winter jet positions to know which regions might face repeated blizzards, ice storms, or atmospheric rivers that can shred power grids. In a stable climate, this whole system wobbles but stays within certain bounds. The equator stays very warm, the poles stay very cold, the circulation cells hum along, and the jet meanders but returns to familiar lanes. That balance is the system working as designed. El Niño is what happens when that balance breaks in the Pacific. Rapid Arctic warming is what happens when that balance frays at the top of the world. What happens to the jet stream when both hit at once? That is the question reshaping America's storm highway right now. Rapid Arctic warming is not a background detail. It is the hand quietly reaching up and grabbing the jet stream by the ankle. In climate science, that hand has a name: Arctic amplification, plain language first. The far north is warming 3 to 4 times faster than the global average. Technical language second. Arctic amplification is the feedback-driven process where ice loss, heat transport, and atmosphere, ocean changes accelerate warming at the top of the world. That is a fact most people hear and immediately forget. Start with the ice. For decades, bright sea ice acted like a mirror, bouncing much of the sun's energy back to space. That balance is the system working as designed. Now, as that ice shrinks, it exposes dark ocean water. The newly open water drinks in sunlight instead of reflecting it. The surface warms. The warm surface melts more ice. The next year there is more dark water, more absorbed energy, more melting. A loop, not a friendly one. As this loop runs, the old temperature contrast between the frozen Arctic and the milder mid-latitudes weakens. The planet's weather engine relies on that contrast. Big difference in temperature means a strong pressure gradient. Strong gradient means a fast, tight jet stream. The science is clear on this. Reduce the contrast, and the jet slows and loosens, like a river losing its downhill slope. Picture that river. When it rushes down a steep mountain, it stays in a relatively straight channel. Give it a wide, flat floodplain, and it begins to snake, carving big S-curves across the landscape. The polar jet over North America is doing the atmospheric version of that. Slower winds aloft allow larger north-south meanders to grow and linger. Ridges bulge north, dragging warm Pacific and subtropical air deep into the continent. Troughs plunge south, pulling polar air over the same towns that were sweating days earlier. Emerging research links this wavier jet to more frequent blocking patterns. In a block, a ridge or trough stops moving and just parks. Under a stuck ridge, heat waves cook the same region for days or weeks, as the 2021 Pacific Northwest heat dome showed in brutal detail. Under a stalled trough, storm after storm rides the same corridor, turning normal rain into prolonged floods or training snow bands into paralyzing blizzards. That energy has to go somewhere. Increasingly, it goes into extremes that simply refuse to leave. So what happens when the jet's traditional anchor in the cold Arctic ice slips, while a hypercharged Pacific is also tugging on its path? If the core temperature contrast that once stabilized America's storm highway is fading, how much faith can anyone put in the old storm tracks, the old planting dates, the old typical winter, or normal tornado season? The next shift in the jet will start to answer that question, and it is already forming just over the horizon. That next shift is not starting over Kansas or over Chicago. It is starting thousands of miles away, in warm water. In a strip of the tropical Pacific that quietly decides how hard the jet stream will punch North America. El Niño and La Niña live there. In plain language, they are long-lived swings in the temperature of the central and eastern tropical Pacific Ocean. When that water runs warmer than average for months to years, forecasters call it El Niño. When it runs cooler for just as long, they call it La Niña. That is a fact most people hear and immediately forget. But that band of warm or cool water is not just a curiosity on a map. It is a throttle on the entire atmosphere. Warmer Pacific water pumps more heat and moisture into the air above it. Colder water does the opposite. That energy has to go somewhere. It goes into wind, into pressure patterns, into the invisible river of air that will eventually decide whether your winter is flooded, frozen, or on fire. In an El Niño year, the Pacific jet stream usually tightens and shifts south. Statement first, technical term second. The result is a stronger, more continuous band of high-altitude wind arcing from near Hawaii into California, the Gulf Coast, and the southern states. That balance is the system working as designed. Storms ride that southern track and tap the extra Pacific moisture, so the southern U.S. often turns wetter. California can trade drought for atmospheric rivers, and the classic storm highway into the Midwest bends and splits. La Niña flips the script. Cooler tropical Pacific water weakens and shoves the jet stream north, favoring a storm track that slams into the Pacific Northwest and then into the northern plains and Great Lakes. The southwest and southern tier are left on the dry, sinking air side of the pattern, watching reservoirs drop while Washington, Oregon, and the Dakotas dig out from heavy snow and pounding rain. El Niño is what happens when that balance breaks. La Niña is what happens when it breaks the other way. For decades, this was the playbook. Farmers, energy traders, emergency managers learned the rough rules. El Niño, expect this. La Niña, expect that. The science is clear on this. These cycles have always shaped American weather. But the background has changed. The Pacific is warmer almost everywhere, almost all the time. The atmosphere above it holds more water vapor. Each El Niño now rides on top of the warmest baseline ocean ever measured. Each La Niña starts from a higher normal too. The same patterns now deliver different outcomes: deeper drought, fatter rain bands, sharper gradients in the jet. And in the last few years, something stranger has emerged. A hyperactive Pacific jet linked to El Niño colliding with a destabilized polar jet bleeding out of the Arctic. Storm paths that look less like classic El Niño or La Niña composites and more like a hybrid the old atlases never drew. So what happens when those two rivers of air stop taking turns and start stacking on top of each other? The answer is already showing up in the radar loops. From orbit, the warning didn't look like a storm at all. It looked like a bruise of heat spreading across the Pacific. Satellites locked onto it first, a broad tongue of unusually warm water stretching thousands of miles along the equator, from the coast of South America almost to Indonesia. The surface shimmered several degrees hotter than average, radiating heat into the atmosphere above like a slow-motion blowtorch. That is a fact most people hear and immediately forget. Forecasters didn't. Because this is the classic El Niño signature, seen from space. A massive pulse of warm water that rearranges the atmosphere. El Niño is what happens when that balance breaks. Trade winds ease, the warm pool sloshes east, and suddenly the Pacific isn't just a background ocean anymore. It becomes the engine room of global weather. Going into this event, the script looked familiar. With that much heat in the equatorial Pacific, forecasters expected a strong Pacific jet. A fast, straight river of air roaring off Asia, loaded with moisture, aimed at North America. Wetter conditions along the southern tier of the U.S., more storms into California, a milder winter for parts of the north. That balance is the system working as designed. But as the season unfolded, the part that made Pacific forecasters lean in wasn't the Pacific jet. It was the polar jet. The Arctic-fed branch that normally arcs cleanly across Canada began to dip, merge, and sometimes phase with the Pacific jet in ways that did not look like the textbook composites. Two rivers of air that were supposed to stay in their lanes started weaving. On the charts, the outliers began to stack up. Sea surface temperatures in key Niño regions spiked to record warm values on top of an already overheated background ocean. Convection, towering thunderstorm clusters anchored over the warmest water, became unusually persistent in the central and eastern Pacific, hammering the upper atmosphere day after day. That energy has to go somewhere. In the models, it carved bizarre jet configurations. Split flows, double jets, and merged cores rarely seen in the historical record. Here is the pattern interrupt. Some of the most important signals never made headlines. Buried in seasonal outlooks, agencies quietly flagged elevated risk of compound extremes. Atmospheric rivers slamming the west coast in tight sequence while, only days later, severe weather outbreaks lit up the plains and south. Not one clean El Niño storm belt, but overlapping hazards, racing across different parts of the country before the last disaster even dried out. So the mood in forecast offices shifted. In Honolulu, in Monterey, in Norman, in Washington, D.C., attention narrowed to a single, unnerving question. What happens when this turbocharged Pacific jet slams into a wobbling polar jet over America? The science is clear on this. When those two collide in just the wrong place, you don't just get rain or snow. You get supercharged storms that redraw the risk map in real time. So what does it actually take to turn a jet stream collision into a storm that wipes out power from Texas to Maine? It starts thousands of miles away. With a very simple, very dangerous number, 1 degree. The Pacific Ocean covers about a third of Earth's surface. Warm it by just 1 degree Celsius, and you are not talking about a pleasant beach day. You are talking about an unfathomable amount of extra heat stored in the water, the equivalent of hundreds of billions of home heaters running non-stop across an area bigger than all the continents combined. That is a fact most people hear and immediately forget. But the atmosphere does not forget. It feels every extra watt. That energy has to go somewhere. The first step in the cascade happens in the deep tropics, over that warm Pacific water. There, the sun superheats the surface, and the water in turn heats the air pressed against it. Warm air rises. Simple. Rising warm air that is loaded with moisture turns into towering thunderstorms that punch 10, 12, even 15 miles into the sky. The technical term is deep convection. You experience it as a wall of black cloud and blinding rain that appears out of nowhere on what was supposed to be a normal afternoon. Inside those storms, water vapor condenses into cloud droplets and raindrops. Every time that happens, latent heat is released. It is the hidden energy that was used to evaporate the water in the first place, now dumped back into the atmosphere at high altitude. That release does not just make the tops of storms warmer. It pumps energy into the upper-level winds, accelerating the flow and helping carve and strengthen the jet streams overhead. El Niño is what happens when that balance breaks. The usual east-west pattern over the Pacific shifts, the warmest water moves, and suddenly the most intense thunderstorm engines are firing in new locations. That reshapes where the jet stream is strongest, where it bends, and where it dives toward North America. Within that river of air, there are narrower rapids called jet streaks, localized maxima where winds can scream past 150 miles per hour. Extratropical heat and latent heat from those storms can intensify nearby pressure systems, deepen storm centers, and tighten the curvature of those jet streaks. The result is more powerful lift over the continent below. That is the invisible hand that can spin up a routine low-pressure system into a bomb cyclone in 24 hours. How do you get a supercell outbreak instead of a rainy day? You supercharge the jet overhead. Now add moisture. A warmer atmosphere holds about 7% more water vapor per degree Celsius. The science is clear on this. In a world with warmer oceans and air, storms riding those energized jets can tap into deeper moisture reservoirs, pulling long, dense plumes of Pacific water vapor into the heart of the continent. That is how an atmospheric river that once meant a helpful snowpack can now mean record-shattering floods. So the cascade looks like this. Extra ocean heat leads to stronger tropical convection. Stronger convection alters jet streams. Altered jets intensify storm systems. And those storms, armed with more water vapor, deliver supercharged rain, snow, and wind over land. It is an energy staircase, and America sits near the top step. The unsettling question is not whether that staircase exists. It does. But how many more steps are being added as the baseline Pacific keeps warming? That staircase does not just lead to bigger thunderstorms over the plains. It also tilts a fire hose of Pacific moisture straight at the west coast. From orbit, it looks deceptively simple, a long, narrow band of clouds stretching thousands of miles from the tropical Pacific into North America. On the ground, it feels like standing under a broken dam. That is an atmospheric river. In plain language, a sky river of concentrated water vapor. In technical terms, a long, focused corridor of moisture transport, often riding along the jet stream like a freight train on rails. A typical atmospheric river can carry more water than the Mississippi at its mouth, but all of it is invisible until it hits land and rises. That is a fact most people hear and immediately forget. The moment that warm, ocean-charged air is forced up over coastal ranges and Sierra peaks, it cools, condenses, and unloads as days of pounding rain and crushing snow. One pattern, many impacts. Now connect that to the jet. When the Pacific jet stream is strong, straight, and aimed at California, it becomes a steering wheel for these aerial fire hoses. That is exactly what happened in the 2023-2024 winter, when a parade of storms slammed into the West Coast. Forecasters watched plume after plume of moisture launch from near Hawaii and slam into the same coastline, swinging large parts of California from drought back to deluge in a matter of weeks. Reservoir managers went from praying for water to racing to dump it safely. But the jet does not only guide moisture, it also sculpts the storms themselves. A sharp bend in the jet, a tight jet streak of 150-mile-per-hour winds overhead, and a strong temperature contrast at the surface can flip an ordinary low-pressure system into something far more dangerous. That rapid deepening has a name, bombogenesis. The result is a bomb cyclone. A bomb cyclone is not a metaphorical term. It is a rapidly intensifying low whose central pressure drops at least 24 millibars in 24 hours, often faster. When that happens under an energized jet, the storm can throw hurricane-force gusts at the coast, spin blizzard conditions inland, and wrap bands of heavy, ocean-fed snow around its core. The science is clear on this. The jet's position and curvature decide where these systems explode and how they track. Picture one of these jet-driven giants making landfall. Coastal cities take on water as storms surge and relentless rain overwhelm drainage. Mountain passes vanish under 10 feet of snow and ice, cutting off entire communities. Hundreds of thousands lose power across 3 or 4 states as heavy, cement-like snow drags down lines and warm, saturated air fuels severe weather on the storm's southern flank. Same jet pattern, different hazards all at once. That balance is the system working as designed. Until the background ocean warms, the jet shifts, and the fire hose starts pointing somewhere new. That energy has to go somewhere. The unsettling question now is where the jet aims next, and which part of America finds itself directly in the crosshairs. So what happens when that fire hose doesn't just point somewhere new, but parks over the same region for weeks at a time? In spring, over the central U.S., that isn't just a pattern shift. That is an assembly line for supercells. Picture a south-shifted polar jet screaming out of the Pacific, diving across the Rockies, and leveling out over Texas, Oklahoma, Kansas, and Missouri. 5 to 9 miles above the surface, winds tear along at 120 to 170 miles per hour. Down near the ground, warm, humid air flows north from the Gulf of Mexico, loaded with water vapor and potential energy. That is a fact most people hear and immediately forget. But when those layers overlap, the atmosphere stops behaving like just weather and starts behaving like a machine. Here is the simple version. You need 3 ingredients: moisture, instability, and wind shear. Moisture comes from that warm Gulf water. Instability comes from strong heating at the surface under cooler air aloft. The jet stream helps provide the third ingredient, vertical wind shear. Winds near the ground blow from the south. A few thousand feet up, they turn southwest. Higher still, under the jet core, they roar from the west. Short right arrow stronger, right arrow strongest. Turning and increasing with height. The technical term is a veering wind profile. That layered shear lets rising air columns start to rotate. A towering thunderstorm with a rotating updraft is called a supercell. Inside it, Air can accelerate upward at highway speeds. The jet vents the storm at the top, pulling air out and letting more warm, moist air rush in at the base. That balance is the system working as designed, until a storm's rotation tightens, tilts toward the ground, and a long-track tornado drills across 3 counties. The science is clear on this. A strong, south-displaced jet in spring increases the odds of those rotating supercells, and with them, violent tornadoes that can stay on the ground for an hour or more. But the jet's influence doesn't stop there. Sometimes, instead of discrete supercells, storms merge into a bow-shaped arc. On radar, it looks like a flexed muscle. On the ground, it is a derecho, a fast-moving complex of thunderstorms that can unleash hurricane-force straight-line winds over hundreds of miles. The same mid-level jet that spins supercells can guide and sustain these systems, turning a single evening squall line into an overnight, multi-state wind disaster. It is the atmosphere's version of a land-based storm surge. Spring 2024 made that painfully obvious. The jet kept reloading over the same corridor from the southern plains into the Midwest. Day after day, warm Gulf air surged north under that roaring river of air aloft. Supercells erupted ahead of the dry line. Derechos ripped east overnight. Insurance tallies started to blur. Billion-dollar hail swaths here, billion-dollar wind scars there. Forecasters stopped asking whether there would be severe weather and started asking which metro area would be in the bullseye this time. So if the jet's preferred spring track is now nudging east or strengthening over new corridors, what does that mean for Tornado Alley? Is the classic Texas to Kansas zone giving way to an emerging Arkansas to Tennessee or even Ohio Valley hot zone? That question is no longer academic. It decides whose building codes, siren systems, and evacuation plans are calibrated for yesterday's risk, and whose are quietly drifting into the path of tomorrow's storms. So what does that shifting bullseye feel like on the ground? It does not feel like a neat migration of risk on a map. It feels like chaos. Meteorologists have a name for it: weather whiplash. Abrupt lurches from one extreme to another, drought to flood, unseasonable warmth to deep freeze, driven by a jet stream that no longer glides smoothly overhead, but buckles, stalls, and then snaps into a new position. That is a fact most people hear and immediately forget, until it happens in their backyard. Picture the American West locked in a multi-year drought, reservoirs ringed with pale bathtub lines, boat ramps ending in dry dust, snowpack thin, soils baked hard by relentless sun. For years, the polar jet stream has arched north, deflecting Pacific storms away, letting warm, dry air park over the region. That balance is the system working as designed until the balance breaks. Then, one winter, the pattern flips. The jet dives south and straightens, turning into a fire hose pointed at the coast. A reconfigured storm highway taps a warmer Pacific Ocean loaded with water vapor. Atmospheric river after atmospheric river slams ashore. The same reservoir system that was inches from dead pool is suddenly racing to keep up, opening spillways, dumping water, watching concrete strain as runoff from parched hillsides arrives all at once. This is not just inconvenient weather. It is a direct hit on the country's food system. Farmers who waited years for rain finally get it, delivered as a barrage of back-to-back storms that erase planting windows. Seeds go into dust, then sit under standing water. Drought-stunted crops that barely survived one season are drowned the next. Intense rainfall hammers hardened ground, ripping topsoil off fields and into rivers. That energy has to go somewhere. It goes into erosion, landslides, and muddy deluges that clog reservoirs that were supposed to be the safety valve. Infrastructure built for a quieter climate starts to fail in predictable ways. Stormwater systems designed around 20th century rainfall statistics are instantly overwhelmed by downpours that now unload a month's worth of water in a single afternoon. Highways buckle or wash out along new storm corridors carved by the shifted jet stream. Rail lines sag over flood-scoured embankments. Power grids get hammered from both sides, heat waves under a stalled ridge of high pressure, then ice storms when the same wavering jet drags Arctic air south over warm, wet ground. 1 week, rolling blackouts. The next, snapped lines and frozen transformers. Pattern interrupt. This is not random bad luck. To the person watching their basement fill or their well run dry, it feels like the weather has lost its mind. To the meteorologist watching the upper air charts, it looks like a jet stream increasingly prone to extremes instead of gentle transitions. The science is clear on this. As the Arctic warms faster and the Pacific pumps extra heat and moisture into the atmosphere, the odds tilt toward sharper kinks, longer stalls, and more violent swings. The question is not whether the next flip will come. It is who will be standing in the wrong phase of the swing when it does. That swing is not abstract. It has an address, a zip code, a mortgage, and a commute. Tens of millions of Americans now live directly under these new bends in the jet stream. The storm highway has shifted a few hundred miles here, stalled a few days longer there, and suddenly neighborhoods that used to be too far north for tornadoes or too far inland for big floods are getting drilled by both. That is a fact most people hear and immediately forget. Consider the numbers hiding behind the headlines. The Southeast and lower Midwest have seen billion-dollar convective outbreaks march along corridors that, on paper, were once low risk. Plains towns designed around occasional blizzards are now taking bomb cyclones that shut down interstates for days. Western valleys that rarely made the news now sit under repeated atmospheric rivers, with warm Pacific water feeding storms that dump a month of rain in a weekend. The jet stream is redrawing the map of where U.S. weather is allowed to be extreme. But the paperwork that runs modern life still assumes the old map is true. Insurance models, FEMA flood maps, local zoning codes, most of them are built on historical storm tracks, historical rainfall, historical wind speeds. That balance is the system working as designed. You pay to manage a 100-year flood. The model says it will probably stay a 100-year flood, and the bank signs off. El Niño is what happens when that balance breaks. A warmer ocean and atmosphere load extra water vapor into every jet-driven storm. That energy has to go somewhere. It goes into taller thunderstorm towers, longer rain bands, sharper pressure gradients. Yet the official maps lag by a decade or more, leaving entire suburbs technically outside the floodplain until the water is literally in the living room. The result is a quiet explosion of underinsurance. Homeowners discover their policies exclude the exact combination of wind-driven rain and surge that shredded their roof. Farmers watch hail and flash floods erase a season's work, only to find that their average loss coverage assumed a calmer jet stream. Municipal budgets buckle as emergency overtime, road washouts, and repeated bridge repairs erase funds that were supposed to go to schools and clinics. And the impacts do not fall evenly. Low-income neighborhoods built on cheap, low-lying land take the brunt of new flood regimes. Rural counties see blizzards and ice storms cut them off from the nearest hospital for 48 hours. While aging housing stock groans under snow and wind loads, it was never engineered to survive. The science is clear on this. The atmosphere is now stress testing the weakest parts of the system first. This is not just more bad weather. It is a fundamental reshuffling of where and how often America's critical systems are pushed to the edge. The question now is not only who gets hit next, but what happens when the jet stream starts targeting the infrastructure that absolutely cannot fail. So here is the uncomfortable question that hangs over all of this. Is the jet stream actually changing, or is everyone just seeing more radar loops on their phone? Because from the ground, it can feel like the atmosphere suddenly went off script right when social media learned how to go viral with every tornado, hail core, and flooded highway. Better satellites, better Doppler, wall-to-wall coverage. Of course it feels louder. The temptation is to say the weather is the same and only the cameras changed. The cameras did change, but the wind did too. High above those viral videos, between about 5 and 9 miles up, decades of measurements tell a different story. Not one storm, not one bad year, decades. Reanalysis projects take old weather balloon launches, aircraft reports, and surface observations and feed them into modern physics-based models, frame by frame, to reconstruct the atmosphere going back to the mid-20th century. Layer on satellite wind profiles from the 1970s onward, and a pattern starts to emerge. That pattern has a name: more frequent blocking. In plain language, the jet stream over North America is getting stuck more often, forming big, slow-moving waves that park heat domes, atmospheric rivers, and winter storms over the same regions for days. That is a fact most people hear and immediately forget. But forecasters staring at those wave patterns see the fingerprints of a system under new stress. So what is pushing it? The science is clear on this. The Arctic is warming 3 to 4 times faster than the global average. The temperature contrast between the warm tropics and the cold pole is the jet's engine. That balance is the system working as designed. Erode that contrast and the jet can weaken, wobble, and meander. At the same time, warmer Pacific and Atlantic waters are loading the atmosphere with extra moisture and energy. That energy has to go somewhere. Scientists debate the exact chain of cause and effect. How much of the extra waviness comes from Arctic amplification? How much from ocean warming patterns? How much from random chaos? But across dozens of studies, there is growing agreement that the background climate signal is now nudging mid-latitude circulation towards sharper kinks and more stalled patterns. Not every extreme is the new climate, but the odds are being quietly, consistently tilted. To track those odds, the monitoring network above your head is far more than a few satellites. Polar orbiting satellites scan wind fields and cloud tops. GPS radio occultation uses tiny delays in satellite signals to map temperature and moisture profiles. Commercial aircraft report wind and temperature along busy flight corridors. Then high-resolution climate and weather models ingest all of it, simulating jet stream dynamics down to individual storm systems. So what is solid and what is still in play? The physics are solid. Stronger horizontal temperature gradients build stronger jets. Warmer air holds about 7% more water vapor per degree Celsius. More moisture means heavier rain and snow when storms form. Confidence is growing that certain extremes, like persistent heat domes and multi-day flood events, are linked to more blocked, wavy jets. But projections of exactly how the jet will behave over specific regions in 10, 20, or 40 years remain an active battleground inside the models. That uncertainty does not mean nothing is happening. It means the atmosphere is changing faster than the old playbooks can keep up. And the next question is brutally simple. How do those shifting winds decide which parts of America get upgraded from bad storms to sustained, system-level assaults? So imagine answering that brutal question while staring at a wall of moving atmosphere in real time. This is what a modern forecast center looks like when the jet stream starts to misbehave. On one screen, global models refresh every 6 hours, repainting the upper-level winds across the entire planet. Color bands snake around the hemisphere, with narrow purple and red ribbons showing 150 mph, jet streaks arcing from the Pacific into North America. On another, upper air charts slice the atmosphere into clean layers, so forecasters can see exactly where that invisible river of air is accelerating, bending, or breaking apart. Then the satellites come in. High above the surface, instruments track tiny motions in clouds and water vapor, turning them into wind vectors. The result looks like someone has combed the sky with white arrows. Those arrows show where the jet is strongest, where it is splitting, and where new storm seeds are quietly forming days before anyone on the ground sees a single raindrop. But satellites only see from above. To fill in the vertical, hundreds of weather balloons are launched twice a day around the world, usually from parking lots and backyards that no one notices. Each balloon carries a small package that measures temperature, humidity, and wind all the way up through the jet level. That is a fact most people hear and immediately forget. Yet those silent profiles are what anchor the models that say whether a weak low will stay annoying or feed on a displaced jet and become a superstorm. Layered on top of that are specialized eyes. Water vapor imagery highlights the dry, striated bands that mark jet cores, especially over the Pacific where ocean storms are born. Commercial aircraft report wind and temperature along their routes, turning every transcontinental flight into a moving weather station. Ground-based LiDAR and radar systems shoot beams into the sky, mapping wind shear in 3 dimensions over airports and major cities. Forecasters use all of this to hunt for anomalies. A jet core 500 miles farther south than normal, a sudden burst to 190 mph over warm coastal water, a stalled ridge locking the jet into a tight, looping pattern. When those upper air distortions line up with moist, unstable air near the surface, alarms go up. This is the window for tornado outbreaks, derechos, or atmospheric rivers that can unload a month of rain in a day. That energy has to go somewhere. The science is clear on this. The system is changing, but the surveillance is not falling behind. There are more eyes on the jet stream than at any time in history. El Niño is what happens when that balance breaks, yet even as patterns grow stranger, the watch only tightens. And the next step is turning that constant watch into specific local warnings before the next line of superstorms lights up the radar. That constant watch matters because right now, in this decade, the jet stream over North America does not look like the one most people grew up with. From space, the last few years play back like a looped disaster reel. Long, glowing plumes of Pacific moisture, atmospheric rivers, slamming the West Coast in train after train. Record winter storms exploding into bomb cyclones, spinning like white hurricanes over the Midwest and Northeast. Then in summer, swollen, motionless heat domes stretching from Texas to the Canadian prairies, baking the ground for weeks. Different seasons. Same invisible highway overhead. This is still the polar jet stream, the storm highway, but the bends are sharper, the stalls are longer, and the timing is wrong. In the 1980s and 1990s, big El Niño winters already twisted the jet into dramatic shapes. Forecasters remember those seasons. The conveyor belt of California floods, the warm, wet East Coast, the stormy Gulf. Now the patterns look like those winters pushed through an amplifier. The waves in the jet dig deeper into the tropics, surge farther into the Arctic, and then just stop. That is a fact most people hear and immediately forget. The pause is the problem. When the jet locks in place for 10, 15, 20 days, the weather under it stops moving. That balance is the system working as designed. A moving jet shares misery around. A stuck jet concentrates it. Look at the background conditions that jet is riding over. The North Pacific has logged record-breaking sea surface temperatures in year after year. A warm pool the size of continents feeding extra water vapor into every passing disturbance. The Gulf of Mexico has hit unprecedented warmth before hurricane season, turning tropical storms into rapid-fire intensifiers within hours of landfall. Farther north, Arctic winters are arriving with far less sea ice than historical norms, exposing open water where there used to be a bright, reflective cap. That energy has to go somewhere. Warmer ocean surfaces mean more evaporation, more latent heat, more fuel ready to be dumped into the upper air. At the same time, rapid Arctic warming is erasing the sharp temperature contrast that once kept the jet tight and fast. The result is a slower, wavier, more easily blocked jet stream that can funnel atmospheric rivers into California one month, then lock a heat dome over the central U.S. the next. The science is clear on this. Some seasonal outlooks now talk about near certain odds of shattering previous rainfall or heat records when particular jet configurations line up over this warmer base state. Recent research papers describe today's extremes not as outliers but as previews. That is the dry, bureaucratic way scientists say. This is the early stage. So the question becomes unavoidable. If this is what the jet stream looks like with just the current level of warming baked into the ocean and air, What do the next 10 to 20 years look like as the system keeps loading with heat? And what happens when this already tilted storm highway collides with the next round of Pacific shocks waiting just beyond the forecast horizon? The answer is, it does not look the same everywhere. A warped jet stream is not a uniform disaster switch. It is a redistribution machine. When the polar jet over North America turns wavier, it stops behaving like a clean, straight storm highway and starts behaving like a looping, stalled conveyor belt. That means one region can sit under the jet's fire hose for weeks, while another is left high and dry under a dome of sinking air. The science is clear on this. A stronger wave in the jet means sharper contrasts on the ground. Picture one arc of that wave locked over the Mississippi Valley. Every few days, another low-pressure system rides the jet, taps warm Gulf water and drags a corridor of deep moisture north. The same towns see supercells, then training thunderstorms, then an atmospheric river-style plume in winter. Fields that were barely dry enough to plant become inland lakes. Levees hold until they don't. Now slide your mental map 1,000 miles west. Under the ridge on the other side of that same jet wave, the air is clear, hot, and stubbornly still. That is a fact most people hear and immediately forget. The same pattern that floods one state can bake another. The ridge suppresses clouds, locks in heat waves, and turns what used to be a bad fire season into a 6-month burn window. Farmers watch storms on radar die at the state line, again and again. This is where preparedness stops being an abstract word and becomes the difference between inconvenience and catastrophe. Along the Gulf and lower Midwest, flood-prone communities live or die by levees, spillways, and the quiet engineers who decide how much water to release from upstream dams. In the Central Plains, the focus is on building codes that assume hail the size of baseballs and tornado winds shredding roofs. Farther north, where a sagging jet can park shallow Arctic air over warm, wet surface layers, the weak link is the power grid facing ice storms that snap lines for hundreds of miles. Then comes the uncomfortable part. Scientists do not fully agree on how much of this new pattern is locked in. Some modeling studies show more frequent blocking events, stalled ridges and troughs that supercharge both floods and droughts. Others emphasize internal variability, the natural chaos in the system, and warn against blaming every freak storm on a single jet stream trend. But uncertainty cuts both ways. It does not mean no problem. It means a wider cone of possible futures, including corridors where supercells, derechos, and winter bomb cyclones line up far more often than the historical record suggests. That energy has to go somewhere. And remember, El Niño is what happens when that balance breaks over the Pacific. The next step is to see what happens when that Pacific-driven jolt meets a jet that is already meandering over America's most built-up storm corridors. America's storm highway has shifted lanes. If you want to understand what that means, you have to stop thinking in state lines and start thinking in corridors. Narrow bands where jet-driven energy, warm water vapor, and local geography now line up more often than they used to. Start with the Mid-South. From eastern Texas through Arkansas, Louisiana, Mississippi, Tennessee, and into western Alabama, the southern jet is dipping in more frequently, riding above a Gulf of Mexico that is running unusually warm. That is a fact most people hear and immediately forget. But that extra warmth means more moisture, more buoyant air, and more fuel waiting for any passing disturbance. The result is a new, hyperactive severe weather alley where supercells, derechos, and nocturnal tornado outbreaks are becoming more common in what used to be considered the off-season. Move west, and the Pacific writes its own chapter. A more energized subtropical jet is now steering atmospheric rivers directly into the west coast, especially northern California, Oregon, and Washington. These are not gentle, soaking rains. These are narrow fire hoses of water aimed at mountain ranges, where the air is forced upward and the sky dumps out. Forecasters talk about integrated vapor transport, residents just see hillsides failing and rivers climbing into living rooms. When the snowpack is deeper and wetter because of a warmer atmosphere, those rivers can stay swollen for weeks. Farther downstream, the same meandering jet sets up volatile winter storms in the northeast. A slight southward dip over the Great Lakes and New England lets Arctic air collide with Atlantic moisture right along the coast. That balance is the system working as designed. But with more ocean heat and higher sea levels, nor'easters and winter bomb cyclones now ride in on a raised baseline. The exact same pressure pattern that once meant a memorable storm can now mean record-breaking coastal flooding from New Jersey to Maine. In the interior, the risk map looks different but just as dangerous. Research points to parts of the Midwest and Southeast. Think Missouri, Illinois, Kentucky, Tennessee, northern Alabama, Georgia, as emerging overlap zones where strong jet-driven wind shear repeatedly sits over deep Gulf moisture. That is prime real estate for tornado and hail outbreaks, including long-track storms that cross multiple states in a single night. Quiet Marches can flip into catastrophic Aprils, with only a small shift in the upper-level winds. And some regions are entering a new rhythm entirely. Fewer storms overall, but the ones that do form are monsters. Long stretches of calm in the high plains or along parts of the mid-Atlantic coast, punctuated by one event that erases a decade of lucky years in 24 hours. Local memory and preparedness erode in the gaps. Then the jet snaps back overhead and reminds everyone that energy never disappears. That energy has to go somewhere. So where are you in this evolving map? Under the southern jet's new severe corridor, beneath the west coast's atmospheric river tracks, inside the Midwest-Southeast overlap, or on a coast where higher water meets stronger winds. The science is clear on this. Your risk is now tied less to a static climate zone and more to where the jet likes to park. In the next section, the focus turns to how to read that in the forecasts you see every day, and what it means for planning the next decade, not just the next weekend. So when you pull up that 7-day forecast and see a quiet map, it is tempting to exhale. No bright reds, no spiraling radar signatures, no screaming jet streaks over your state. It looks calm. But calm in this climate does not always mean safe. Sometimes it means loaded. Think of the atmosphere, ocean system as a giant compressed spring, or a bow pulled back and held. Warm water in the Pacific and Atlantic, warm ground across the plains, warm air pooled over the Gulf of Mexico. All of it is quietly adding potential energy to the background state. That energy has to go somewhere. It does not just disappear because the jet stream parked itself a little north of you for 2 weeks. Under a blocking pattern, the jet stalls, kinks, and loops. High pressure sits over one region, low pressure over another, and the usual storm highway shuts down. That balance is the system working as designed, heat trying to move from the tropics toward the poles, moisture trying to condense and fall out. But when the pattern locks in, the transfer slows. Heat and humidity stack up near the surface, especially over warm ocean water and dark, sun-baked land. You feel it as a muggy stretch, a weirdly warm winter week, or an endless gray dome. Forecasters see something else, a growing reservoir of instability. Long strings of 70-degree January afternoons across the south. Gulf dew points in the mid-70s in April. Ocean temperatures several degrees above normal feeding an atmospheric river off California. That is a fact most people hear and immediately forget. On the model screens, it looks even more unnerving. For days, the pattern stays almost motionless. Then a shortwave rides the edge of the block. The jet suddenly digs, and the whole setup snaps like a released spring. A quiet central U.S. map turns into a week of back-to-back supercells and derechos. A sleepy Rockies pattern flips into a historic chain of bomb cyclones racing along a re-energized jet, burying one region in snow while flooding another with warm rain. Forecasters talk about stored CAPE, about latent heat in the ocean, about snowpack waiting to melt. Different language, same idea. The system is charging up. El Niño is what happens when that balance breaks over the Pacific. A shifted jet is what happens when that broken balance gets exported over American soil. What keeps people in the forecast offices up at night is not only the tornado outbreak they can see 3 days out. It is knowing the ceiling is rising, the maximum strength, rainfall rate, and wind speed the atmosphere can now produce when the right jet configuration finally clicks into place. To understand how that hidden energy moves, piles up, and then erupts along the jet, you have to go below the surface, into the ocean's own waves and currents that are already tugging on the atmosphere from underneath. And those are far stranger than the weather maps you see on TV. What you see on satellite loops, the spiraling cloud shields, the sharp jet streaks, the exploding supercells, is just the wallpaper. Impressive, violent, and loud, but still only the outer skin of a much deeper machine. The real driver is beneath the waves. Every flash of lightning over Kansas, every atmospheric river slamming California, is connected to how warm water is arranged in the Pacific. Not just at the surface, where the colors on a sea surface temperature map glow red and orange, but hundreds of feet down. That is a fact most people hear and immediately forget. Buried under the Pacific's surface are vast subsurface heat pools, immense blobs of warm water trapped below the mixed layer, stretching for thousands of miles along the equator. Think of them as hidden reservoirs under the ocean's floor of motion, not literally on the seafloor, but locked beneath the cooler surface veneer. They can sit there for months quietly, while forecasters argue about short-term weather at the surface. Then they move. These structures do not wander aimlessly. They organize. They line up along the equator, guided by Earth's rotation and the basin's shape, and begin to slide east like a slow underwater conveyor belt. A massive pulse of warm water the size of a continent is moving across the ocean interior right now. Scientists call it a Kelvin wave. A Kelvin wave is essentially an underwater pulse, a lens of anomalously warm water trapped against the equator, racing east at nearly 300 miles per day, depressing the thermocline as it goes. In plain language, it shoves the boundary between warm surface water and colder deep water downward, shutting off the usual supply of cold upwelling in the eastern Pacific. That balance is the system working as designed. El Niño is what happens when that balance breaks. When one of these Kelvin waves reaches the eastern Pacific and that buried heat pool finally surfaces, the ocean's skin temperature can jump by several degrees in a matter of weeks. That energy has to go somewhere. It surges into the atmosphere as extra evaporation, extra water vapor, extra buoyancy for storm clouds. The science is clear on this. From space, all you notice is that the cloud bands shift, the jet stream bends, and the storm tracks over North America suddenly look wrong. On the ground, you notice your once-in-a-century flood showing up twice in a decade. Here is the pattern interrupt. The atmosphere over America's heartland this year is being shaped by a pulse that started thousands of miles away, deep under the Pacific, months ago. To understand how that underwater Kelvin wave helps launch superstorms over the United States, you have to follow that hidden battery as it discharges, upward from the ocean interior, through the sea surface, and into the high-altitude river of air that is already shifting overhead. That hidden battery does not release its power in a neat, gentle exhale. It moves like a slow-motion underwater tsunami, a rolling bulge of warm water sliding along the equator, invisible from the surface but absolutely real. A massive pulse of heat, the size of a continent, is already on the move. Scientists call it a Kelvin wave. Picture that for a second. Not a breaking wave you'd see on a beach, but a long, low swell of warm water trapped along the equator, hundreds of feet deep, stretching for thousands of miles. It creeps east across the Pacific at roughly 300 miles per day. No roar, no spray, just a silent rearrangement of where the ocean stores its energy. That is a fact most people hear and immediately forget. To make it less forgettable, imagine a giant waterbed filling an entire stadium. Someone leans hard on one end. The surface dips under their weight, but on the far side, a bulge of water slowly rises and slides away. That traveling bulge is the Kelvin wave. In the real Pacific, the push is not a person, it is the trade winds. When those winds blow hard from east to west, they pile warm surface water up near Indonesia and press the deeper warm layer downward in the west. That balance is the system working as designed. Strong trades, warm water stacked in the western Pacific, cooler water upwelling in the east, jet stream patterns that, while chaotic, are at least familiar. El Niño is what happens when that balance breaks. When the trade winds weaken, or even briefly reverse, the piled-up warm pool near Indonesia is no longer pinned in place. It sloshes east as a Kelvin wave, like an underwater freight train of heat. As that wave travels, it pushes the thermocline, the boundary between warm surface water and colder deep water, downward along its path. The warm layer thickens and deepens, especially in the central and eastern Pacific. Cold upwelling is choked off. The surface begins to warm fast. Forecasters watch this progression in real time, first as a subsurface anomaly on their charts, then as a widening smear of red on sea surface temperature maps. When that buried warm pool finally reaches the central and eastern Pacific and rises toward the surface, it can flip the entire tropical weather engine. Thunderstorms shift eastward, towering convection erupts where the ocean used to be relatively cool, and the high-altitude winds above them respond. That energy has to go somewhere. The science is clear on this. Those rising plumes of warm, wet air punch into the upper atmosphere and start tugging on the jet stream itself. A pulse of heat that began as an invisible Kelvin wave along the equator can, months later, bend the storm highway thousands of miles away over North America. How does an underwater bulge in the tropical Pacific end up deciding where a blizzard forms over Chicago or where a supercell spins up over Texas? That is where the jet stream enters the story and where the stakes jump again. Follow that pulse of heat forward. It starts when the trade winds over the equatorial Pacific ease off, just a little at first. Normally, those winds shove warm surface water toward Indonesia, piling it up like a sloshed bathtub. That balance is the system working as designed. But when the trades weaken, the pile relaxes. A massive lens of warm water slides back east along the equator as a slow, subsurface surge. A pulse of heat with a name. Scientists call it a Kelvin wave. As that Kelvin wave arrives in the central and eastern Pacific, the warm water rises, the thermocline drops, and the surface heats up several degrees above normal. Suddenly, the ocean between Hawaii and South America is not just warm, it is loaded. That energy has to go somewhere. It goes up. The extra heat and moisture pour into the atmosphere, feeding taller, more persistent thunderstorms in places that are usually quieter. Those thunderstorms are not just bright blobs on a satellite loop. They are vertical conveyor belts of energy. As warm, wet air rises and condenses, it releases latent heat high in the troposphere. That is a fact most people hear and immediately forget. But where that heat is released acts like a thumb on the scale of the entire circulation system. Shift the storm clusters 500 or 1,000 miles east, and you shift where the atmosphere gets its biggest daily injections of power. That displaced heat release stretches and tilts the Hadley and Walker cells over the Pacific, the giant overturning loops that move air from the equator toward the poles and back. El Niño is what happens when that balance breaks. The altered circulation can strengthen the subtropical jet stream, aim it differently, or both. Instead of a gentle, wavering ribbon, the Pacific jet can sharpen into a focused, 150-mile-per-hour hose of wind screaming eastward 5 to 9 miles above the surface. Once that hose is locked in, it starts to interfere with the polar jet. Sometimes it undercuts it, driving a low, fast branch of wind straight into California, supercharging atmospheric rivers that unload record rain and snow. Other times, it merges with the polar jet, then dives southeast, carving a deep trough over the central United States. That trough is the launch ramp for supercells over Oklahoma, derechos across the Midwest, and blizzards wrapping up into bomb cyclones off New England. So the chain runs like this. An underwater bulge of warm water creeps east, surfaces, ignites new thunderstorm zones, shifts where the atmosphere vents its heat, reshapes the circulation cells, retools the jet streams, and finally redraws the storm tracks over your house. The science is clear on this. What is not clear yet is how far this particular jet stream break will go, or what happens if the next Pacific shift yanks the storm highway even harder out of place. When that storm highway kinks hard enough, it doesn't just move rain around. It can unlock the Arctic. High above the pole, there is a vast, spinning pool of cold air and low pressure. In plain language, it is the atmosphere's deep freeze. In technical language, it is the polar vortex. That is a fact most people hear and immediately forget. But this one structure quietly controls whether your winter feels normal or biblical. Most of the time, the polar vortex is fenced in by a tight, fast polar jet stream. Picture a circular river of wind racing around the Arctic, 5 to 9 miles above the surface, keeping the worst of that air locked away in the far north. That balance is the system working as designed. The temperature contrast between the warm mid-latitudes and the brutally cold Arctic powers that fence and keeps it fairly round. Now run the tape forward into a warming world. The Arctic is heating up 3 to 4 times faster than the global average. Sea ice is shrinking, dark water is exposed, and the region is holding more heat it never used to keep. That energy has to go somewhere. As the north warms, the contrast that drives a strong, straight jet weakens. The polar jet becomes wavier, slower, easier to shove around by random pulses from the Pacific and Atlantic. When that happens, the fence around the freezer starts to sag. Lobes of the polar vortex can bulge southward, like cold air fingers reaching down into mid-latitudes. A massive pulse of Arctic air diving into the central United States is not a quirky headline. It is a displaced lobe of the vortex, riding a distorted jet stream straight into your backyard. February 2021 in Texas was the case study that finally made this real for millions of people. A wildly contorted jet stream carved a deep U shape over North America. On the west side, warm Pacific air surged north. On the east side, a chunk of the polar vortex plunged all the way down into Texas and the Gulf Coast. Arctic air poured over land that usually worries about heat waves, not blizzards. Then it hit moisture. That dense, bitter air collided with humid Gulf water vapor and lifted it, wringing out freezing rain, sleet, and snow over a region built for mild winters and quick thaws. Power plants froze. Natural gas wells locked up. Wind turbines iced over. Roads turned to glass. It was not just a cold snap. It was a winter superstorm, engineered by a broken jet and a displaced vortex. Events like this are the paradox of climate change. The background is warming. The ocean and atmosphere are loading up with extra water and energy. And yet the occasional outbreak of brutal cold can become more intense in specific places. The science is clear on this. Arctic warming is disrupting the jet and the polar vortex in ways that raise the risk of rare, severe cold blasts even as average winters trend milder. So no, a Texas freeze does not disprove warming. It is one symptom of a larger, unstable system. The real question is what happens when those same jet distortions stop dragging down cold and start locking in heat, rain, and rotating superstorms over the same regions again and again. And start locking in heat, rain, and rotating superstorms over the same regions again and again. Climate models have been running that future on fast forward for decades. The picture they paint is not subtle. As the Arctic warms 2, 3, even 4 times faster than the global average, the temperature contrast between the poles and the mid-latitudes weakens. That contrast is the fuel that keeps the polar jet tight, fast, and mostly west to east. That balance is the system working as designed. So what happens when that balance breaks? Models answer with the same broad storyline: continued Arctic amplification, a softer gradient between cold north and warm south, and a jet stream that, on average, loses some of its straight-line punch. The science is clear on this. Mean mid-latitude westerlies are projected to weaken slightly, especially in the upper troposphere, but the averages are not what keep forecasters up at night. Because buried inside those simulations is a pattern you can feel in your backyard. As the jet's overall speed eases, its path becomes more vulnerable to sharp kinks, deep meanders, and high-amplitude waves. In technical language, more blocking patterns. In everyday language, the jet stream gets stuck. A ridge parks. A trough refuses to leave. Whether that should move on in 2 days lingers for 2 weeks. Many climate models now show an increased likelihood of these persistent ridges and troughs over North America and Europe. A locked-in ridge over the western U.S. can bake the region in relentless heat, drying out soils until any spark turns into a megafire. A stubborn trough over the central U.S. can keep the storm track pinned over the same states, feeding supercells, derechos, and training bands of warm, water-loaded air that dump catastrophic rain. That energy has to go somewhere. If this sounds familiar, it should. Recent decades have delivered real-world previews. The 2021 Pacific Northwest heat dome under a monstrous blocking ridge, the stalled jet during Hurricane Harvey's record-shattering floods, the looping, contorted flow linked to Europe's repeated summer heat waves and winter floods. That is a fact most people hear and immediately forget, but modelers notice the rhyme between simulations and the sky. To be clear, there is no perfect agreement. Different models disagree on exactly where the jet will slow the most, how often specific blocking zones will form, and how strongly the Atlantic and Pacific Oceans will tug on the pattern. Some runs show dramatic changes, others show more modest shifts. Yet the direction of travel is remarkably consistent, toward a more capricious, high-impact jet stream environment. So the forecast is not a neat, linear story of weaker jet, fewer storms. It is a story of a wobblier jet, more stuck patterns, and higher odds that when the atmosphere decides to do something extreme, it keeps doing it. The next question is how that translates into concrete risk maps for the places people actually live. So what does a wobblier, more stubborn jet actually feel like in your life over the next decade? Not as a diagram on a forecast model, but as headlines, insurance claims, and days your town never really forgets. Start with winter. Picture more seasons where the term atmospheric river shows up on your phone alerts every other week. Long, warm plumes of Pacific moisture slamming into the west coast, then curling inland along a shifted jet and unloading over the Rockies, the Midwest, even the Northeast. A massive fire hose of water in the sky. Then, when that jet dips and intensifies, those same plumes turn into bomb cyclones, rapidly deepening low-pressure systems that spin up blizzards, coastal floods, and hurricane-force gusts in 48 hours. That energy has to go somewhere. Spring does not calm down. It migrates. The classic tornado alley in the Central Plains gives ground to new corridors in the Mid-South and Lower Ohio Valley, as a south-displaced jet overlaps record warm Gulf water and juiced humidity. 1 week, supercells rake Arkansas and Tennessee. The next, a derecho rides the jet's core from Kansas to Chicago, toppling transmission lines designed for a quieter 20th century atmosphere. That is a fact most people hear and immediately forget. Then summer arrives and breaks the illusion that extremes are a season. A stalled jet ridge bakes Texas and the Southwest for weeks, while a downstream trough parks over the Mississippi basin. On one side, relentless heat domes, dried-out soils, reservoirs shrinking. On the other, training thunderstorm bands that turn creeks into inland seas overnight. Flood on one interstate, dust storm on the next. Same continent, same month. In that world, new normal is not a slogan. It is a statistical reality. Storms that used to be labeled once in a generation start penciling out as once in 20-year or even once in 10-year events in the actuarial tables, especially where the jet's kinks repeatedly focus moisture and wind. The science is clear on this. Warmer air and ocean water load the atmosphere with more fuel. The jet just decides where to cash it out. There are regional winners and losers. although winter becomes a relative term. Parts of the northern tier may see milder winters with less persistent Arctic air, but pay for it with higher winter flood risk and heavier wet snow when bomb cyclones clip through. Some interior western valleys may get fewer major storms overall, yet when the pattern finally aligns, deep trough, tropical moisture feed, stalled jet, the result is a catastrophic flood rather than a gentle soaking. Infrastructure is the quiet character in this story. Bridges rated for 1960s flood heights, storm drains sized for storms that no longer exist, power grids that assumed ice or heat, not both in the same fortnight. That balance is the system working as designed. The problem is, the design is out of date. If communities are already straining under today's superstorms, what happens when the jet spends more years in these high-impact configurations? The next part of this story asks an even harder question: who adapts in time, and who gets left exposed when the storm highway shifts again? So how do you tell if your town is about to sit under that new storm highway or right in the breakdown lane? You do not need a supercomputer. You need one map that most people never look at. Pull up a jet stream chart, specifically the 300 millibar wind map. That is the level about 30,000 feet up where passenger jets cruise and where the polar jet roars. On NOAA, the Weather Prediction Center, or many TV station sites, you will see colored wind bands arcing across the continent. The tightest, strongest ribbon, that is the jet core. That is the conveyor belt steering the next round of extremes. Start with shape. When that ribbon plunges far south over the western or central U.S., you are looking at a deep trough. Plain language, cold, high-altitude air from the north is diving into the middle of the country. Scientists call this a more wavy jet. You can call it a warning. That energy has to go somewhere. Now look at direction. If the strongest winds over the Pacific are blasting straight into the west coast, like a fire hose aimed at California, Oregon, or Washington, forecasters start using another phrase: atmospheric river. A long plume of warm, ocean-fed moisture rides along that jet, slamming into mountains and lifting into torrents of rain and snow. That is a fact most people hear and immediately forget, until the hillside above their neighborhood starts to move. Shift your eyes downstream. See a bright, narrow segment of very fast winds arcing over the plains or the Mississippi Valley. That is a jet streak. When that jet streak sits above warm, humid air near the surface, the atmosphere becomes primed for severe weather. Rising air below, accelerating winds above, wind shear tearing storms into rotating supercells. Tornado outbreaks and derechos love that configuration. Then there are the patterns that do not move. On the same maps, you may notice a big bulge of higher pressure that just sits over the southeast or Greenland or the North Pacific, forcing the jet to bend around it. That is a blocking high. It can pin a blizzard over the same corridor for days or lock a fire weather pattern over the same region week after week. The science is clear on this. More blocked jets mean more stuck disasters. Pattern interrupt. Now imagine you never looked at that map again. You would still get your local forecast. You would still see winter storm warning, flash flood watch, tornado emergency crawl across the screen. But without the jet, it feels random. With it, the warnings start to make sense. A deep trough over the Rockies, heavy snow and blizzard risk on the cold side, severe storms on the warm side, a screaming Pacific jet aimed at the coast, flood watches, mudslide alerts, avalanche danger. This is weather literacy. Pair the big picture jet map with your local forecast, and the chaos turns into a readable signal. That balance is the system working as designed, at least for your understanding. In the next section, the view zooms back out again, from your browser window to the entire hemisphere, to see how these same patterns decide which regions become permanent superstorm corridors, and which are left in the deceptive calm just outside the lane. So what does life actually look like when your town ends up under that new storm highway? Not in a model. In real streets, with real basements filling with warm brown water at 3 in the morning. Start in the west, where the jet's supercharged atmospheric rivers have been slamming into the coast like freight trains made of Pacific moisture. One mid-sized city, think Sacramento, but it could be half a dozen others, watched back-to-back 100-year floods overtop levees designed when Elvis was still on the radio. The old system assumed storms would pass quickly and politely. They did not. That is a fact most people hear and immediately forget. City engineers did not. They are ripping up 20th century blueprints, raising levees, carving new overflow basins, and rebuilding stormwater networks with bigger pipes, smarter pumps, and more room for water to spread out without taking homes with it. Cross the plains and you hit a different problem. In the Midwest, it is not walls of water, it is walls of wind. One small town in Iowa took 2 derechos and multiple tornado outbreaks in 5 years, each one tracing that same wavy jet pattern overhead. Roofs peeled. Grain bins crumpled like soda cans. The old building code had been written for thunderstorms, not 120-mile-per-hour sideways debris. Now new homes require hurricane clips, stronger anchoring, and impact-rated garage doors. The school doubles as a hardened community shelter with interior safe rooms, backup power, and doors that actually close against pressure waves. Tornado drills are no longer once-a-year rituals. They are treated like fire, predictable, deadly if ignored. The grid is learning the same lesson. Jet-driven winter storms that flash freeze rain on the lines, followed by record heat waves that cook transformers, have turned once-in-a-generation outages into a subscription service. Utilities are spending billions to harden the system, undergrounding key corridors so ice cannot pull them down, adding redundant loops so one snapped line does not black out an entire county, and upgrading equipment to handle both deep cold snaps and brutal heat without failing at the exact moment everyone needs it. That energy has to go somewhere. If the lines cannot carry it safely, it finds the weakest point and breaks it. Out in the fields, adaptation looks quieter but no less radical. Farmers are shifting crop varieties to those that can handle late spring freezes and late season flash droughts on the same acre. Planting dates are sliding around the calendar as forecasters warn that the jet's new configuration can flip from deluge to dust in a week. Investments in soil health, cover crops, reduced tillage, better organic matter, turn the ground into a sponge that can drink sudden downpours and hold moisture through long dry spells. That balance is the system working as designed, at least for the farm. None of this touches the jet stream itself. The science is clear on this. No levee, code, or substation can straighten the river of air 5 miles above your head. But how communities build, plan, and rehearse can turn a superstorm from a mass casualty event into a long, miserable week. The next question is obvious. Who gets to adapt in time, and who is still pretending the old climate calendar is coming back? But even if a community admits the old calendar is gone, there is another hard truth waiting. Some of the most dangerous jet-driven superstorms will still arrive a little sideways from what the models promised. From space, the polar jet over North America looks clean and surgical, a sharp ribbon of 150-mile-per-hour wind carving out storm tracks. On a forecast map 3 days out, it can look just as neat. That is a fact most people hear and immediately forget. On the ground, the reality is messier. Shift that ribbon by 50 miles, delay a surge of Gulf moisture by 2 hours, cool the surface by one unexpected outflow boundary, and you do not just move the rain. You can change the entire character of the storm. Forecasters can often see the dangerous pattern coming. A screaming jet over a warm ocean, deep Pacific moisture feeding into the plains, a strong temperature gradient across the Midwest. The broad signal is clear. This is a loaded pattern. But the exact way that warm, humid air rises into towering thunderstorms depends on processes the models still blur together. Convection is lumpy, chaotic, and fast. A single cluster of storms can grab energy from the jet, punch higher into the atmosphere, and then reshape the wind field that was supposed to steer it. This is feedback in real time. A thunderstorm complex matures, dumps cold water, and sends a gust front racing ahead. That boundary becomes the new focus for rotating supercells. Those supercells tug on the jet above them, locally strengthening it, which in turn helps them spin harder. That balance is the system working as designed. But capturing that dance hour by hour, county by county, is still beyond even the best global models. So the forecast might say, severe storms likely, and then the atmosphere quietly upgrades that to historic. An expected strong cyclone crossing the Rockies suddenly deepens 15 millibars faster than projected, slamming the high plains with a bomb blizzard. A day flagged for scattered tornadoes blooms into a sprawling outbreak, because one jet streak overlaps surface instability just a bit farther east than anticipated. Forecasters are not surprised there is a major event. They are surprised where the bull's eye lands. Layer on a changing climate, and the uncertainty stretches even further. The jet is operating over warmer land and warmer water than in the past. The Pacific and Arctic are pushing the mid-latitude atmosphere into regimes with very few historical analogs. Models trained and tuned on the old climate are now being asked to simulate a new one. The science is clear on this. That energy has to go somewhere. So when a forecast sounds fuzzy on exact totals but confident about risk, that is the moment to pay attention. In a loaded climate with a warped jet stream, the ceiling on how bad a given pattern can get is higher than before, even if the floor looks familiar. The next problem is not just that storms can surprise forecasters. It is who gets left exposed when the surprise is baked into the new normal. That is where the myths rush in to fill the gap. When the forecast ceiling keeps rising, the internet starts looking for a simple villain. Enter the drunk jet stream. A wobbly ribbon of air, staggering across the map, tipping cold into Texas and warm air into Alaska. It is a vivid image. It is also a meme that quietly rewires how you think about the physics. The jet is not actually drunk. It is responding to changing temperature contrasts, to warm oceans, to a climate system that is being pushed outside its old boundaries. In a stable climate, the polar jet stream is tight and fast, racing 5 to 9 miles above North America, often over 150 miles per hour. That balance is the system working as designed. Strong cold in the Arctic, milder air to the south, a sharp gradient that keeps the storm highway roughly on track. El Niño is what happens when that balance breaks in the Pacific. A similar idea applies here. Change the gradient, change the river of air. Arctic temperatures are climbing 3 to 4 times faster than the global average. That is a fact most people hear and immediately forget. But it matters, because it eats away at the temperature difference that helps anchor the jet. A weaker contrast can mean a slower, wavier jet that loops south, stalls, or locks in place. Forecasters see those kinks connected to events like the Pacific Northwest heat dome and long-lived flood patterns over the central U.S. Here is the catch. Not every brutal storm, tornado outbreak, or atmospheric river is because the jet stream changed. The science is clear on this. Any given supercell over Oklahoma still depends on local wind shear, surface moisture from the Gulf, and how warm the boundary layer gets that day. The jet can load the dice, but it is not the only player at the table. Some scientists argue that much of the apparent jet stream weirdness can still be explained by internal variability. In plain language, the atmosphere has always had wild years. Others point to emerging evidence of more blocked patterns in a warming backdrop. Both can be true. The system is noisy, and the long-term warming signal runs through that noise like a bass line under chaotic drums. So what should you watch for? Look for explanations that connect a specific event to clear mechanisms. A sharp jet streak over the Rockies, wrecked Guam Pacific or Gulf water feeding moisture. A stalled ridge locking heat or rain in place. Beware of vague claims about crazy weather with no mention of gradients, moisture, or jet configuration. And resist the fatalism baked into the drunk jet jokes. A more extreme jet environment does not mean helplessness. It means the risk map is being redrawn. That energy has to go somewhere. Building codes, floodplain maps, insurance models, and evacuation plans decide whether it turns into headlines or history lessons. The next question is who updates those systems fast enough, and who pretends the storm highway has not already moved. And here is the uncomfortable part. That redrawn storm map is not random. It is being traced over a planet that is already running a fever. Day to day, weather looks chaotic. One city floods, another freezes, another bakes under a heat dome. It feels like noise. But underneath that noise, the baseline has shifted. The oceans are warmer, the air is moister, the Arctic's ice cover is thinner and more fragile than at any point in modern records. That is a fact most people hear and immediately forget. Those background conditions are the canvas the jet stream is painted on. Warm more of the ocean, especially the Pacific and Atlantic, and the whole atmosphere holds more water vapor. About 7% more water in the air for every degree Celsius of warming. That balance is the system working as designed. Evaporation, condensation, rainfall, repeat. El Niño is what happens when that balance breaks in a very specific part of the Pacific. The jet stream shift is what happens when that balance bends almost everywhere at once. When the air is warmer and wetter, every stalled jet stream kink becomes an opportunity. A slow-moving thunderstorm line over the Midwest now has access to far more water, so it dumps 15 inches of rain where 8 used to be the worst case. A winter storm tapping Atlantic heat can bomb out into a blizzard that shuts down 3 states. A summer ridge that refuses to move can turn a hot week into a lethal 3-week heat wave. The dice are still rolling. They are just loaded. Scientists have started putting numbers on that loading. Attribution studies take a specific disaster, a 1 in 1,000 year flood in Kentucky, a Pacific Northwest heat dome, a cluster of billion-dollar derechos, and run climate models with and without human-caused warming. The results are blunt. Some heat waves are now dozens of times more likely. Some rain extremes are 30 to 50% wetter. The science is clear on this. The jet stream's twists and stalls matter, but the extra energy in the system decides how brutal the final outcome is. So this is not a story about crazy weather on one channel and climate change on another. It is the same story. The shifting jet is one of the main delivery systems that turns abstract greenhouse gases into flooded basements, failed crops, and shattered power grids. That energy has to go somewhere, and right now it is going into supercharged storms, surprise freezes, and record-breaking heat landing in the same regions, sometimes in the same year. The bigger problem is perspective. It is easy to feel like a spectator, watching radar loops and viral clips of overturned semis. But this is not a movie. This is a live experiment in atmospheric physics, and human emissions are the control knobs. The highways of the sky are being rebuilt in real time. The question is not whether the experiment continues. It is how much more extreme the results become, and who decides when to hit the brakes. So what does any of that actually mean for you, standing on a driveway, staring at a sky that now flips from blue to violet in an hour? The highways of the sky are being rebuilt, but your house, your street, your routines are still parked on the old map. The first move is brutally simple. Know your hazards. Not the generic version, the precise version. Are you in a river basin that has quietly flooded 3 times in 10 years? On a windswept ridge where 80-mile-per-hour gusts are becoming normal? In a snow belt that now swings from bare ground to 4 feet of wet cement in a weekend? Or in a city where warm spell now means back-to-back 100 degrees? That is a fact most people hear and immediately forget. Yet the jets knew. Wavier path is sorting America into zones of flood, wind, snow, and heat, and the boundaries are moving. Local emergency managers, flood maps, and insurance data tell a blunt story. That balance is the system working as designed. El Niño is what happens when that balance breaks, when Pacific water and atmosphere shove the storm track into places it rarely lingered before. The science is clear on this. Where the jet repeatedly stalls, extremes stack. Once you know your likely hit, you can build a resilience kit that matches it. Not a bunker, just a buffer. If your threat is days of grid failure in a heat dome or winter bomb cyclone, that might mean a small battery power station or generator charged ahead of time, plus a way to keep one cool room or one warm room livable. If the risk is atmospheric river flooding, it means stored water, shelf-stable food for several days, critical medications in one grab-and-go bag, and a written communication plan so family knows where to meet when cell towers and social media feeds go dark. That energy has to go somewhere. During jet-driven superstorms, it often goes into breaking the systems you usually rely on. Hardening your home is the slow, unglamorous version of heroism. Tie down or store outdoor furniture that can become airborne projectiles. Improve drainage so water flows away from foundations instead of into basements. Trim trees that overhang roofs and power lines before the next derecho does the pruning for you. When renovating, ask bluntly, can this be raised above flood level, strapped for higher winds, or insulated against more brutal heat? Small upgrades now are cheaper than rebuilding in a new climate later. Information is its own form of shelter. Use reliable forecast sources, not whatever goes viral. Enable emergency alerts. Learn the difference between a watch and a warning so you know when to think and when to move. In a world where the atmosphere is less tied to the old seasonal playbook, timing is everything. None of this is panic. It is adaptation to a warmer, more energized system. The question is, how far can personal resilience go when the jet itself keeps bending into new shapes, and who decides what happens when the local fixes are no longer enough? At some point, the jet is acting weird, stops being a curiosity and becomes a choice. Not a choice about the weather tomorrow, a choice about what the jet stream is allowed to do to your life over the next 30 years. Because yes, the jet has always wobbled. There have always been blocking patterns, surprise blizzards, out-of-season severe weather. That is a fact most people hear and immediately forget. But the long, slow loading of this system with extra heat is not random. The science is clear on this. The background warming that is bending those waves sharper and stalling them longer is driven by human greenhouse gas emissions. Think about what that means for the Arctic. The region that used to be locked in ice and cold is now warming 3 to 4 times faster than the global average. That balance is the system working as designed. A huge temperature contrast between the frozen north and the warm tropics keeps the polar jet tight and fast. Erode that contrast with decades of emissions, and the jet slackens, meanders, and gets stuck over North America in ways that keep superstorms parked over the same towns. Here is where the fork in the road actually is. Different emissions pathways are not abstract policy debates. They are different jet stream futures. Rapid cuts in carbon pollution keep Arctic warming closer to just disruptive. Business as usual pushes it toward unrecognizable. In one path, warmer oceans still feed powerful storms, but the odds of the most extreme, contorted jet configurations stay lower. In the other, extra ocean heat and a thicker blanket of greenhouse gases mean more blocked patterns, more flood than drought whiplash, more winters where the polar vortex takes an extended vacation in your backyard. That energy has to go somewhere. Right now, a lot of it is going into warmer water, higher sea surface temperatures, and a juiced atmosphere that can hold more moisture. Policy is the quiet lever that decides whether that energy is met by 1950s infrastructure or 2050s infrastructure. Updated building codes that assume 150-mile-per-hour jet-steered wind events, not 90. Drainage systems sized for today's atmospheric rivers, not yesterday's rainstorms. Buyouts and relocation support for neighborhoods hit by the same jet-locked flood 3 times in 10 years. And there are co-benefits that show up long before the jet stream calms down. Cutting emissions from power plants and traffic cleans the air in your lungs this decade, even as it reduces the chance your grandkids watch another billion-dollar derecho roll over 3 states in an afternoon. Better transit, tighter homes, more urban trees. Those are climate policies and public health upgrades at the same time. So no, the jet stream story is not destiny. It is a warning label on the trajectory the system is currently on. The atmosphere is telling forecasters where the road leads if nothing changes. Collective choices, local votes, national standards, global agreements decide how sharp that curve becomes and how hard the next superstorm hits when the jet decides to test every weak point it can find. So step back for a second and replay the whole story in your head. It started with something you never see. A narrow river of air, 5 to 9 miles above the surface, more than 150 miles per hour, quietly steering almost every major storm that hits the United States. That is a fact most people hear and immediately forget, until the day their roof is in the neighbor's yard and the jet stream is suddenly the only term anyone is saying on live TV. In its calmer state, that band is simple to describe. Cold, dense Arctic air to the north, warm, lighter air to the south. The sharp temperature gradient between them creates a pressure gradient, and the atmosphere answers with wind. That balance is the system working as designed. The jet runs fast and relatively straight, a stable storm highway arcing from the Pacific into the heart of the continent. But the gradient is changing. The Arctic is heating 3 to 4 times faster than the global average. The ocean is warmer, the background atmosphere is loaded with more water vapor, and the once clear line between cold and warm air has blurred. That energy has to go somewhere. It now goes into sharper kinks, deeper dips, and more stalled loops in the jet stream. Layer on the Pacific. El Niño, La Niña, and the warm pools of water they move around do not just sit at the surface like a bathtub you forgot to drain. Their heat rises into the atmosphere, shifting whole belts of rising and sinking air, launching Kelvin waves, and nudging the jet north or south by hundreds of miles. El Niño is what happens when that balance breaks over the equator. The broken pattern then echoes all the way into the polar jet over America. Suddenly, the opening montage looks different. That chaotic night of sirens, rotating wall clouds, and a derecho carving a 600-mile scar of shattered windows across the Midwest was not random. It was a specific jet configuration, an amplified trough digging into abnormally warm Gulf moisture, a screaming upper-level wind maximum overhead, a stalled block upstream, running over a climate system that had more heat and water to spend than it used to. This is the core reality. America's storm highway has moved and destabilized. The same invisible current that once delivered familiar winter storms and predictable spring fronts is now capable of parking an atmospheric river over California for a week, then flipping and firing supercells over Tennessee in February. The science is clear on this. So when the sky over your house turns green at dusk, when winter rain turns to ice in a single hour, you are not just unlucky. You are standing under the downstream end of a rearranged jet. In a world where the sky itself is changing, knowledge is one of the few forms of shelter everyone can share. The next question is brutally simple. Knowing this, what do you build, protect, and demand before the next configuration locks in overhead? So the next time the sirens sound, you will not just be hearing noise. You will be hearing the shape of the sky. Boiled all the way down, this story has 3 anchors. The jet stream is your storm highway. Climate change is reshaping its path and behavior. That shift is turning more storms into superstorms. That is a fact most people hear and immediately forget. You do not have to. When a radar image explodes into reds and purples over your state, remember what is really moving. 5 to 9 miles above the surface, a band of wind that can top 150 miles per hour is steering that line of storms like a freight train on rails. That balance is the system working as designed. A strong temperature contrast between the warm tropics and the cold Arctic keeps the highway tight and fast. Now remember the oceans and the ice. The Arctic is warming 3 to 4 times faster than the global average. The Pacific and Atlantic are storing record amounts of heat. That energy has to go somewhere. It does not stay politely in the water. It bleeds upward into the atmosphere, bulging the jet stream into deeper waves, slowing it down, making it stall. The highway kinks. The exits move. So when you hear a meteorologist call a flood a once-in-a-century event or a winter bomb cyclone unprecedented, connect the dots. Ask, what were the oceans doing? How far had the sea surface warmed? How weak was the Arctic cold pool that week? You are not just unlucky under a random monster. You are living under a rerouted river of air. The science is complex. The practical message is not. Extremes are becoming more likely in new places in the wrong seasons. Tornado outbreaks racing along a jet that has sagged south in February. Atmospheric rivers slamming cities that never planned for Pacific-style rain. Heat domes parking over regions that used to count on reliable wind. The science is clear on this. The patterns are shifting faster than the memories built on the old ones. So pay attention to patterns, not just headlines. One storm is a disaster. 10 storms tracing the same warped jet stream is a warning. When you talk about crazy weather at work or over dinner, nudge the conversation one step deeper. Ask what the jet stream was doing. Ask how warm the ocean was. Talk about risk. Talk about resilience. Dry, small talk about the weather has always been a social habit. Now it is also a survival skill. By staying with this story to this point, you have already invested time and focus in your own safety and understanding. Treat that like preparation, not paranoia. Because the final step is deciding what to do with that knowledge before the next siren sounds, and before the next configuration of the sky locks into place. Preparation only matters if it continues. The jet stream is not going to pause its experiment with the atmosphere while everyone catches up. This channel exists to track that experiment in real time. Think of it as a guide along America's storm highway, following the polar jet 5 to 9 miles above the surface as it kinks, stalls, and reloads. Each new loop in that river of air is a decision point. Who gets the next supercell outbreak? Who gets the next atmospheric river? Who spends the next week under a heat dome instead of a cold front? Here, the goal is simple. Connect the breaking weather in your feed to the deeper climate signals driving it. When forecasters say the jet stream is acting drunk, that is not just a colorful quote. That is a fact most people hear and immediately forget. Episodes on this channel slow that down, unpack what a wavy, unstable jet actually means, and show how warm Arctic air, a charged Pacific, and record ocean temperatures are all tugging at the same high-altitude rope. If staying ahead of the next superstorm season matters to you, this is the moment to lock in. Hit subscribe, turn on notifications, and build a habit of checking in before the next line of red radar echoes lights up your phone. There are full deep dives here on atmospheric rivers flooding the West, heat domes baking the central U.S., and El Niño reshaping the Pacific storm tracks that feed straight into the American jet. Those longer explanations are competing in an algorithm that rewards quick, shallow clips. A 30-second video of a semi blown off a highway will always be easy to recommend. Long-form breakdowns of how the jet stream moved that storm there need a push. Likes, comments, and shares are not vanity metrics in this context. They are levers that tell the system to surface more weather literacy instead of just more disaster footage. So add your voice. Leave a comment with what the last year of weather has looked like where you live. Stalled rain bands, back-to-back derechos, snow where there never used to be snow. Ask the questions that the local forecast never quite answers. Those patterns and those questions shape future episodes, turning this channel into a network of people watching the same river of air from thousands of different ground-level angles. The science is clear on this. The jet stream will continue to shift as the planet warms and the Arctic races ahead. That energy has to go somewhere. No one can reach up and straighten the storm highway back into place, but understanding how it bends makes you far less likely to be blindsided when it does. Stay with this, because the next segment goes one step further, from tracking the highway overhead to mapping the specific regions on the ground that are moving into the bulls. So pull back one last time. The continent shrinks. The cities dim. The camera lifts through the thin blue shell of the atmosphere until the whole hemisphere hangs in frame. A glowing ribbon of wind encircles the planet 5 to 9 miles above the surface, a pale, electric band tracing the boundary between warm and cold. That is the jet stream, the true storm highway. From this height it looks smooth, almost gentle. That is a fact most people hear and immediately forget. So the view holds a beat longer and the illusion starts to crack. The ribbon is not a circle. It kinks, it dips, it loops south over the Pacific, then whips back north over North America, dragging clouds behind it like a wake. Now the zoom begins. The lens glides toward the United States as the band of wind tilts and writhes. Each bend is a temperature contrast. Each dip is a tongue of polar air sliding south, meeting air that has been warmed by dark ocean water and bare ground where snow used to sit. Each sharp turn is a pressure gradient loaded with energy. On the map, it is just another contour line. On the ground, it is someone's flooded street, someone's snow-buried car, someone staring at radar at 2 a.m. hopping the Hook Echo passes a few miles to the north. Every line up there is a story about heat, ice, and motion. Every kink is a decision point the atmosphere makes in real time. That balance is the system working as designed. El Niño is what happens when that balance breaks. The science is clear on this. The jet stream will keep shifting in the years ahead. Arctic air will keep warming faster than the mid-latitudes. The Pacific will keep throwing off strange patterns that forecasters scramble to decode. But understanding will shift too. Models will sharpen. Satellites will see more. Warning times will grow by minutes, then hours, then days if the investment is there. So here is a small ritual. The next time you open a weather app, do not just check the icon over your city and move on. Take 10 extra seconds. Swipe to the big picture map. Look for the sweeping arcs of cloud and the colored wind bands and ask quietly, where is the jet today and what is it aiming at? Over time, that question rewires how the sky looks. A line of storms is no longer random. A surprise blizzard is no longer a surprise. That energy has to go somewhere, and you can start to see where it is most likely to land. Hold that final image, the hemisphere turning in darkness and daylight, the jet glowing faintly as it steers storm after storm across the ocean and over the land. The sky is changing. But if you keep watching, learning, and preparing, you do not have to face it in the dark. Because the next pattern is already forming beyond the horizon. The only real mystery left is who will be ready when it arrives.